Hello students, I hope you're having a good day today. Welcome to the second lecture for Module 4. Today we're going to talk about the independent sample t-test. So the independent sample t-test is much like the paired sample t-test, except our observations are no longer dependent on each other, so we're not going to measure observations more than once. In fact, we'll only measure them once. So just like a paired sample t-test, we don't have any population information. We don't have population parameters. We don't have means and standard deviations in the population. And so we have to make an inference based on samples. And so we'll compare two samples to each other where each of those samples are being inferred to larger populations. Now the difference in an independent sample t-test and a paired sample t-test comes from the samples themselves, or what we call independence. What makes an independent sample t-test different than a dependent sample t-test is that our samples are independent of each other. And what we mean by that is that every observation is measured once and only once. And so in a paired sample t-test, remember the observations are measured twice, and then we can subtract those observations from each other to get a single sample of different scores. But we can't do that with an independent sample t-test. And the reason why is because every observation is different from every other observation. And so we can't directly subtract observations from each other. So what you need to remember that in an independent sample t-test, the samples are independent of each other. The observations in those samples are independent of each other, both within the group and between the groups. And so we call this a between groups design. And you'll remember that term from the last lecture, that a paired sample t-test has dependent groups or a within groups design, whereas an independent sample t-test has independent groups, or what we call a between groups design. So to review, an independent sample t-test is what we call a between groups design. That means that each observation, whether it be a person or a thing, is measured once and only once, and they fall in one and only one of the samples. So if I have Bill, he's selected for my study, I measure him on some construct, on some dependent variable. Bill's only going to be in one of the samples. He's not going to be in both samples. He only have a score in one and only one of the samples. So when this happens, we say that each score for each person or thing is independent of any other score, both within the sample but also between the samples. And that's what we mean by a between groups design. Because each observation is independent of any other observation, this introduces variability into our data set. And so you remember from earlier lectures, we've talked about variability quite a bit, that if I increase variability, then I decrease the reliability, which in turn decrease the validity or the accuracy of my statistical test. And so whenever given the choice between a paired sample t-test and an independent sample t-test, we would always prefer to do a paired sample t-test. And the reason why is because the observations are dependent on each other across the two samples. So if I have Bill and I measure him twice, well, everything about Bill is the same except for those two measurements. And so I can subtract those two measurements from each other and get a different score. I can't do that in an independent sample t-test design. That the people in one of my samples are completely different than the people in the other sample. And so I can't subtract the scores from each other. That the people in one of my samples, in one sample, has many different characteristics than the people in the other sample. In fact, people differ from each other in an infinite number of ways. And so I can't directly subtract people from each other across the two samples. And because I can't do that, that increases the variability in my data. So as a review, both dependent and independent sample t-tests compare one sample to another. Now it's important to remember that even though we're comparing samples with the actual data, we're still inferring to two populations. So one sample is being inferred to one population, the other sample is being inferred to the second population. And so we're comparing the populations to each other, but we're doing that through the measurement of the samples. So as a review, the dependent sample t-test is a paired sample t-test. It has within subjects designs. Our observations are being measured twice, and because each observation is measured twice, we're able to subtract from those observations from each other. In the independent sample t-test, we have a between groups design where every observation, every person or thing is measured once, and they're in either one or the other sample. So if you remember from the previous lecture, we talked about SAT scores with or without a prep course. So let's take a look at that again, and let's talk about an independent sample between subjects design. So you'll recognize this slide from the previous lecture. So here we have our between groups design. Now it's important to note that when we say between groups or between subjects, we're talking about the same thing. So here's our between groups to between subjects design. And you'll notice here that they're independent of each other, that we have different participants in each of our groups. We have one group, which is the no prep course group, and it has Samantha, Greg, and Olga in it. And then we have the other group, the prep course group, and has Jethro, Ginger, Denise, and Jim. And so notice here that the subjects are completely independent of each other, that there's nothing that's relating Samantha with Jethro or Ginger with Samantha or Olga with Denise. They're completely different independent observations or people. And so we can't subtract their SAT scores from each other. We have to treat them separately. And so even though we can't subtract their scores from each other, we can get a mean for each group. So in other words, I can take Samantha, Greg, and Olga's SAT scores, I can average them and get a mean for the no prep course condition. I can also do the same thing for the prep course condition. I can take Jethro, Ginger, Denise, and Jim's scores and add them together and divide by 4 and get an average for the prep course condition, in which then I can compare the two groups to each other through their means. And that's what you have to do with the between groups design, is that you can't compare the individuals within the groups to each other, but you can compare the group means from each of the groups to each other. Now let's talk about the assumptions behind an independent sample t-test. And we know by now that every statistical test that we run has a certain set of assumptions. So let's go through the ones here. So you'll notice right away that the first 3 are the same 3 that you've learned so far for every hypothesis test. In fact, most of our parametric tests have these same 3 in common. And so once you memorize the first 3, they're going to be pretty much the same through most of the tests that we learn. So those 3 are: the dependent variable should be scale, the participants should be randomly selected from the population of interest, and the populations should be normally distributed. Now again, we don't have population information, so we have to infer or assume based off of the central limit theorem whether or not we are meeting that populations are normally distributed assumption. So the last 2 are new and are unique to the independent sample t-test. So participants should experience one of the independent variable conditions. So we've already talked about that. What we're saying is that our observations should be in one and only one of the samples, or one and only one of the groups. And so we shouldn't have the same people in both groups, but rather both groups should be completely different people. So we don't have any dependency among our observations. The last assumption is that the population difference between means should be 0. Now this is similar to the paired sample t-test. If you remember, with the paired sample t-test, we said the population mean difference is 0. So the idea is the same. The difference is in the wording. So in an independent sample t-test, we're saying difference between the means, and we say that because we can't subtract the individual scores from each other. We can only subtract the means of the groups from each other. So we find the difference between the means rather than the mean difference. And so when we say mean difference, we're saying we're subtracting the observations from each other. And we're not doing that here. So the last assumption is that the population distribution between the means should be 0. This again is based on the null hypothesis, that if our intervention has no effect, then the means of both the groups should be the same. And if they're the same and we subtract them, we should get 0. Let's take a closer look at the last 2 assumptions. So the fourth assumption is that participants experience one level of the independent variable. Now we've talked about that already, as that our observations are independent across the samples, but there's another question that we need to answer. The question we need to answer is, how do we assign the observations to the levels of the independent variable? In other words, how do we determine which participants end up in which of the 2 samples, or which of the 2 groups? Now there are many ways that we can assign our participants to the groups, but the 2 that we'll be concerned about in this class is convenience assignment and random assignment. And so we've talked about convenience and randomness before in terms of selection, so this is going to be a little bit different, but the idea is generally the same. And what I mean by that is that we can assign our participants to groups conveniently. So maybe I put an ad out saying I'm doing a study, and the first 25 participants that show up, I put them in the no prep course condition if we're using the SAT example, and then the next 25 I put in the prep course condition. Well, that would be a convenient assignment. However, I have to be worried that those who show up first may be more motivated, may be more interested in study than those that came later or in the second half of that group. And now all of a sudden I have more than just the prep course that varies between the two samples. I have prep course and motivation and interest, and so now I have 3 explanations for any findings that I may get. And so convenience assignment is not the best way to assign our participants to two groups. The other way that we can assign is through random assignment. In other words, we let chance decide who ends up in which group. And the easiest way to do this, if you have 2 groups, is just to flip a coin, so that every single person that you're going to have in your study has an equal chance of being in either one of the groups. And what this does is that it equates the 2 groups to each other. In other words, the participants in each group should be equivalent to each other. So everything that may be different between the 2 groups cancels out, and the only thing that you're left with is the manipulation. So in this case, if we're looking at SAT and prep courses, our 2 groups, if we use random assignment, should be the same on all possible characteristics except for the one of interest. In this case, whether or not they have a prep course or don't have a prep course. So to go back to our example, if we have Samantha, Greg, and Olga, and they were conveniently assigned to the no prep course condition, and Jethro, Ginger, Denise, and Jim were conveniently assigned to the prep course condition, then I wouldn't know for sure that it's the prep course that caused the difference in the SAT scores. It could be that Jethro, Ginger, Denise, and Jim were the first to show up for the study, and therefore they ended up in the prep course condition, and Samantha, Greg, and Olga showed up to the study later, and so they end up in the no prep course condition. And so Jethro, Ginger, Denise, and Jim in the prep course condition could also be more motivated, or maybe they're just more timely, and that transfers to higher SAT scores. And so I wouldn't know for sure that the difference in SAT scores is because of the prep course. It could be because of increased motivation, it could be because of timeliness, because they're more interested in the study, whatever it may be, but it's not necessarily the prep course. So I want to make sure that that's not those confounding variables are not in my study, and so instead I might flip a coin. So if Samantha shows up to my study first, I flip a coin. Heads, she's in the no prep course condition. Tails, she's in the prep course condition. We flip the coin, she gets heads, she ends up in the no prep course condition. Greg shows up and we flip the coin, we get heads again. He's in the no prep course condition. Jethro then shows up, we flip a coin, he gets tails, and so Jethro's in the prep course condition. And so you get kind of the idea that now, because the coin is deciding who's in what group, every person has an equal chance of being in each group. And if that's the case, then all the individual differences between the 2 groups should be the same, with the only difference being the prep course or lack of a prep course. And if that's the case, then we can reasonably conclude that the differences in the SAT scores is due to the prep course or lack of a prep course, not due to any other individual difference or any other confounding variable. Now you want to make a note to ensure that you know the difference between assignment and selection. So we talk about random and convenient assignment and random and convenient selection, but it's important to note that they're talking about 2 different things. And so this is something that you'll need to know for the future, is that when we talk about selection, we're talking about selecting or sampling from a population. So we have a larger population that we're interested in studying, and we either randomly or conveniently select from that population to get our sample. Now once I have that sample, I then can assign 2 levels of the independent variable, and that's where we talk about assignment. And I can assign either conveniently or randomly. So if I assign conveniently or randomly, now I'm talking about making sure that my 2 samples or my 2 groups are equivalent on all possible individual differences except for the one that I'm interested in studying. So if I'm interested in studying prep course or no prep course, I want the 2 samples or the 2 groups to be absolutely equivalent, or as best as possible equivalent, so that when I get a difference, I can attribute it to the lack of or the inclusion of a prep course, and not to any other individual difference. So make sure you note the differences between assignment and selection. Selection, we are sampling from a population. Assignment is when we take our sample and we divide it into groups, and each participant in our sample has an equal opportunity to be in either group, so that our groups are equivalent to each other on everything except for the variable that we're manipulating, in this case the independent variable. Now let's take a look at the very fifth assumption: the population difference between means is 0. And I mentioned before that this is similar to the paired sample t-test's fifth assumption, that the population mean difference is 0. So the idea is the same, but how we get there is a little bit different, and so we should talk about that conceptually. We are introducing a new distribution. This is the fourth distribution that we've learned this semester. So we've learned about the population distribution of scores, and that's when we're getting z-scores, or in other words, we're looking at individuals compared to a population. We've talked about the population distribution of means, and that's for a single sample z-test or a single sample t-test, and that's when we're looking at a sample compared to an overall population. Then we learned about the population distribution of mean differences, and that's for a paired sample t-test. And again, that's when we don't have any population information and we can compare two samples to each other where those samples are dependent on each other. In other words, observations are being measured in both samples. And then the new one, the one that we're learning right now, is the population distribution of differences between means. And that's for an independent sample t-test when our samples are independent of each other. So the distribution of differences between the means has the same characteristics as a distribution of mean differences. So the distribution will look the same as a paired sample t-test, but how we get that distribution will be different conceptually. So this distribution is centered at the null hypothesis, where the difference between the means is 0. So for example, in our SAT example that we've been working with, that our null hypothesis is that there's no difference in SAT scores with or without the SAT prep course. So what we're saying is that if our prep course has no effect, then the difference between the means should be 0. If it has no effect, then the SAT scores and the no prep course condition and then the prep course condition should be the same. And so when we subtract them, we should get 0. When we draw out our distribution, here's what it looks like. And so you'll notice it looks like our other t distributions, that it's a bell-shaped, it's a normal distribution, it's unimodal, it's symmetrical. It also extends to infinity in both the positive and the negative direction. And you'll note that the difference between the means is centered at 0. Mu sub m diff equals 0. So at that same point, the t statistic for our distribution is a t of 0. And then we extend in both directions in terms of standard error, in both the positive and the negative direction. And so that's where we get our values of 1, 2, and 3, and negative 1, negative 2, negative 3. That if I have a negative 3 in my t statistic, what I'm saying is 3 standard errors below the difference between the means of my two groups. Let's go ahead and go back to our SAT example. So here's a between groups design, independent sample t-test design. And we have our two groups, they're independent of each other. And so in the population, we would expect that the differences between those with no prep course and those with a prep course, the difference would be 0 between the means. And so here again, so here's our samples. So it's not our populations. We're inferring from our samples to the population. So we can get an average for each of the samples. And so in the no prep course condition for Samantha, Greg, and Olga, the average SAT score is 1,000. And for the prep course condition for Jethro, Ginger, Denise, and Jim, the average in our sample for the prep course condition is 1,025. So we can use both of those values to infer back to the populations, where we have one population with no prep course and the other population with a prep course. So we can take the means of our two groups, where one is the no prep course condition and the other is the prep course condition, and we can subtract them from each other. So we'll take 1,000 and we'll subtract 1,025, and we get a difference between the means in our samples of negative 25. What's that saying is that in the no prep course condition, the SAT scores are 25 points lower than in the prep course condition. Now this becomes our best estimate for the population difference. So we can take this negative 25 and we can now compare it to the distribution of differences between means in the population, which we said we assume to be a difference of 0. We still need to account for variability, but we can now make a comparison between our samples to the samples based on the research hypothesis to the null hypothesis difference between means of being 0. Now let's account for that variability by using our t-statistic formula. So note here we have several different symbols, and you should know what each of the symbols represent. We have m of x and m of y. Those are the sample means for both of our groups, so the mean for one group minus the mean of the other group. We then subtract the population mean differences, which is mu of x and mu of y, and then we divide by the standard error pooled. So the sub p there stands for pooled. What we're saying there is that we're combining the standard error between the two groups. Alright, so what standard error pooled is the estimated standard error in the populations. Okay, so we know something about the quantities of mu x minus mu y. That's the difference between the means in the population. And if you remember, based on the null hypothesis, we can assume that that difference is 0. Because we can assume the difference between the means and the population is 0 based on the null hypothesis, we can remove that portion of the equation. And so now we're left with the sample means for x and for y, or in other words, each of our groups, subtracting the sample means of each of our groups, divided by the estimated standard error pooled in the population. As you can see from the t-statistic formula, we need to calculate the standard error pooled. And so the reason why we're getting a standard error pooled is because we have independent samples. That each of these samples are independent of each other. We can't combine the samples directly by subtracting scores like we could in a paired sample t-test. So that means we got to calculate the standard error for each of the samples. And so our formula for doing that, in order to combine the two different standard errors for the two samples, is that we'll take the variance pooled, that's s squared sub p. So you should make a note here that s squared tells us it's variance, it's not standard deviation. So make sure you put in the variance pooled into your formula. And we're going to divide that variance pooled by the respective sample sizes of each of the groups. And so this weights the variance pooled to the size of each of the samples. Because our samples are independent of each other, we could have unequal sample sizes. In other words, the number of observations or people in each group may be different. In one group we may have 3, in the other group we may have 10, or we may have 5 and 15. And so we need to account for the fact that the sample sizes may be different from each other. Once we take those variance pooled and we divide by the respective sample sizes of the samples or of the groups, then we take the square root, and that'll get us the standard error pooled. So you're probably saying to yourself, how do I get the variance pooled for my standard error pooled formula? And so here's that step right here. And so if you look at this equation, it looks a lot more daunting than it really is. Just realize what we have here is the variance for x. That's the left half of the formula. And then we have the variance for y, which is the right half of the formula on the right side of the equal sign. So all we're really doing is getting the variance for x and the variance for y, and we're essentially adding it together. And so that's how we get our variance pooled, is literally we are combining the variances for both of our samples, sample x and for sample y. Once we have that sample variance pooled, we can plug it into our formula for standard error pooled. Then we can place that standard error pooled in our formula for the t-statistic. So that's how we'll get our t-statistic. Notice that our t-statistic here is very similar to the t-statistics that we've calculated previously. We're getting the difference of two means and we're dividing by a measure of variability. That format will stay pretty much the same throughout the semester. And so we'll change the symbols and change how we get those values for those symbols, but the formula is very, very similar. Alright, so in class we will go through an example of an independent sample t-test from start to finish so that you'll be able to apply what you've learned here to an actual statistical test. Alright, I'll see you in class. Thank you.